Okay, let me start by thanking ICTS for inviting me to give this talk. So this talk will be on the subject of bulk entanglement entropy. This is in the context of ADS-CFT. This addresses a question which is different from some other questions about entanglement entropy in ADS-CFT, which have been asked before. So let me explain. So this work was, part of it has been published recently in a work with Shumit, Anurag, and Sandeep. So let me start. All right. So let us consider, the usual setup of ADS-CFT, in which we consider an asymptotically ADS theory, which is holographically dual to a certain boundary theory. Now consider an arbitrary spatial subregion of the bulk, such as this. Can people see my cursor? Hello?
Yes, we can see it.
Thank you. So such as this, and so this spatial subregion I'll call A. And the question that we'll ask is, what is the entanglement entropy of this region A, which is defined in the bulk? Okay. Now, let me just say at the outset that this is different from the Ryuta-Kayanagi problem, which discusses the entanglement entropy of a spatial subregion, say little a, like this, of the boundary theory. Okay. And the bulk dual of this is given by the area of an extremal surface in the bulk, this, which is anchored to the boundary of this A, which is a spatial subregion of the boundary theory. So in this case, the boundary theory, the spatial subregion is, let's say, this is some p-dimensional spatial space of the boundary theory, and the surface is also p plus 1 dimensional. Okay, so this is different from what we are asking. So we are asking the question of a spatial subregion A, which is d minus 1 dimensional, where d is the total dimension of the bulk spacetime. And there is a boundary theory, which is dual to this, which is p-dimensional. And typically, like in the case of D3 branes, okay, there is this S5, which is part of the ADS5 plus S5, which does not correspond to a spatial subregion of the n equals 4 super Yang-Mills theory that's in here. Okay, so this bulk subregion may not have anything to do with the spatial subregion of the boundary theory. In particular, we will come to, so we will look at the example of D0 branes in some detail, in which P will be equal to 0. It doesn't have any space at all, but there the bulk will be, the usual 9 plus 1 dimensional space-time, and we can consider some 9-dimensional subregion in this bulk, which we will identify with the target space of this D0 branes. But let's wait and watch. So this is the game. The question we ask can be split into two parts. One is that whether there is an example, there is a definition in the bulk itself of this entanglement entropy of a bulk subregion. That's number one. And secondly, and we will have a concrete proposal for that, what does it correspond to in the boundary theory? So let's take these two issues in turn. So the intrinsic definition of a bulk entanglement entropy, if there is any. So a priori it is not clear in a theory of dynamical gravity how to define the entanglement entropy of a subregion with its complement because of the dynamical gravity. except perhaps when the bulk theory or certain regions of it can be described in terms of weakly coupled perturbative fluctuations of gravitons and other fields on a background space-time metric. Okay, so this would be a limited understanding of what the bulk entanglement entropy could be. So we would have a non-perturbative exact definition in terms of a boundary theory later on. But this is one way one could try to define it. So note that we are talking about gravity here. One could also address similar questions in string theory itself, and you know, like in a manner which was done in the paper by Atish Dabolkar in 1994, or written recently about entanglement entropy in string theory. We're not going to discuss this in today's talk. Now, from the perturbative viewpoint, so what one is talking about is some perturbative graviton and some other fields riding on a given space-time background metric. And one would expect that the leading behavior of the bulk entanglement entropy would be given by the area of the boundary of this subregion A divided by some appropriate cutoff. Here we have denoted, as I have said already, the dimension of the bulk spacetime to be D, so that the bulk subregion A is D minus 1 dimensional, and its boundary del A is D minus 2 dimensional, and epsilon is an appropriate UV cutoff of the bulk theory. Now, in a theory of gravity, which is embedded in a UV finite theory, such as string theory, one expects the above quantity to be finite, with epsilon replaced by an appropriate quantity, such as the string length or the Planck length.
So, sorry, Gautam, can I ask a question? What is the definition of the entanglement entropy in a theory of gravity?
Yeah, good. So one definition, you know, which is probably the sort of most zeroth order definition, is that you think of the think of the background metric to be something given, and there are bulk fields, you know, riding on, like scalar fields or gravitons riding on this background. And then you can you know, simply think of the entanglement entropy calculation in normal way that you would do for field theory in Gauss space.
But then that's a free field calculation which does not involve any dynamical gravity.
It does not. It does not. So
yeah,
that is certainly true. So the you know, dynamical gravity is only appearing here in the sense of perturbative gravitons. So of course, because of these reasons, and for many other questions in gravity, you know, we would like to sort of state them and address them in the boundary theory. Okay, so that's the great thing about ADS-CFT, that it allows us to, I mean, if you believe in ADS-CFT, it allows us to sort of address these questions in the boundary theory, and which is what we will do. But at the moment, as you said, this does not indeed take into account dynamical gravity as such, except in the form of perturbative gravitons.
Okay.
So yeah, so one question about the cutoff. So in a theory of gravity which is embedded in a UV finite theory, such as string theory, one expects the above quantity to be finite, with epsilon replaced by string length or Planck length. In a holographic theory, we expect the finiteness to do with the finiteness of n. We will in fact see this explicitly in the context of the example of the C equal to 1 matrix model, which we'll discuss in briefly. Now about the area.
Hello?
Yes.
Sorry. So is this correct to say that, you know, like even when you're talking about just gravitons, free fields, there is some subtlety associated with how you impose the Gauss constraints and so on.
That is right. That is right. So
even the free theory, it's a bit subtle to define what you mean.
Indeed, the subtleties about there is the linearized page invariance, and one has to deal with that. And one is assuming that one would use one of the sort of techniques that people have used so far in defining entanglement entropy in Gauss field. Is that you're absolutely right? Yes.
Okay, Gautam, can I ask one question?
Yeah.
Hi. Hi. You said that the finiteness, on the one hand, from the string theory side, you are saying that either the Planck length or the string length is the cutoff, right? And the matrix model, you are saying that it has to do with finiteness of n. But if we start with an ADS CFT and then take the flat space limit,
right?
We take n to infinity, right? But still, string length and Planck lengths are finite.
Yeah.
Right? So there is a contradiction between these two.
Yeah, basically what we will find is that it will, what will appear in this place of epsilon to the power d minus 2 is the Newton constant. So that is what I essentially want to say. Yeah, you were saying that, of course, the Toft coupling lambda and n are independently variable quantities, and I could take. Is that what your question is?
Yeah, exactly. That I can keep G fixed, the coupling constant, and then take the n to infinity.
Right.
That's the flat space limit, right?
Yes. Yes. Yeah. So maybe I should say it is the combination which appears in the Newton constant, which will appear as the cutoff. So, yeah. So they so that here it is. So what I'm going to say is that so first of all, let's measure the area in the Einstein metric because it's a natural notion of a metric which is duality invariant. And we will conjecture that the appropriate cutoff is given by Newton's constant, G, and to be precise, the epsilon is related to the Planck length. And to be precise, it is area. So we are going to say that it's not only G, but we are also going to put in that 1/4 there. Okay, this is conjectural, of course. And the constant 1/4 is inspired by the Bekenstein bound and the version suitable for spatial region, that is. And for a pure state, okay, this is how we think about it. For a pure state, the entropy of a region A can be regarded as coming from entanglement with its complement, and Bekenstein bound that can be interpreted by saying that the entanglement entropy cannot exceed the right-hand side of the above equation, which is the equation 1, which is the Bekenstein bound. So our conjecture here is that the bulk entanglement entropy saturates this bound. Okay, so so a similar conjecture was made by Bianchi and Myers on some different grounds in 2012.
Sorry, Gautam, I'm confused again about the setup, because now that G Newton has appeared, presumably there's some relevance of dynamical gravity. But now I'm confused about the definition once again. I mean, earlier when we were just looking at free gravitons, it made sense.
Right.
But I'm confused about how we can, I mean, if you have dynamical gravity, there are many questions which appear. For instance, what is the gauge invariant definition of this region itself, this bulk region, how one defines that? And other questions, including, the fact that gravity might localize information very unusually. One instance where, for instance, such a formula might run into trouble is, let's say you take a region that just hugs the boundary. So you're an ADS.
Okay. And
you take a small band which goes very close to the boundary, but extends from R equal to R0 all the way up to infinity.
Okay.
So it covers the whole sphere, but goes from R equal to R0 to infinity. Then this region, includes also a patch of the boundary theory. it's not an entanglement wedge of anything. And you would have expected that its entanglement actually is 0. And because it, do you see what I'm saying? Because it's like taking the Ryu-Takenagi surface, but now taking the entire boundary. So there are at least some cases where one might worry about the validity of this formula in general. I mean, for some cases, I guess it would be correct where A is an entanglement wedge of some region in the boundary, but for some other cases, I mean, if it's a very general formula, I would be worried.
Yeah, no. Actually, let me say that we are certainly not saying that it's so in our setup we are thinking of, first of all. So here are the qualifiers that first of all it's a static geometry, and secondly it's a spatial subregion. A is a spatial subregion on the time slice with respect to which the geometry is static. So,
but that may not be enough. I mean, let's take just the vacuum of ADS.
Yes.
And let's take the time slice t. Let's set it up in global coordinates, and let's take the time slice t equal to 0.
Okay.
And now let's take the region that goes from r equal to r naught, where r naught can be any value you like, all the way up to r equal to infinity.
Yes.
Now the boundary theory lives at r equal to infinity of this region. All operators in the boundary theory you can obtain as limits of operators in the bulk as r goes to infinity.
Yes.
And one of the points that we were discussing, in this last talk and last day, was that the entanglement entropy of this region is 0 because this region contains all information about the bulk. So even though you might have thought that it has a finite area at r naught, and you might have thought there's an area, there's an entropy proportional to r naught, just r naught to the d minus 2. But it's I mean, in this case, because of the way gravity localizes information, it would not work. Now, maybe there's a way in which you can make the area of this 0. I would be worried if this was a.
No, I see this. So that's certainly this is an interesting, this is an important point. And so you're saying that what if it sort of covers everything all the way up to the island?
Exactly, all the way up to infinity, all the way up to the boundary, right? So it's like there's a disk inside which you have cut out, and there's a region outside. Now,
so we certainly have to qualify for situations like that. Yeah, that's an important point, Suvrat.
Gautam, can I ask a question which actually doesn't rely on holography but might be related? Is your surface supposed to be convex? Is there any convexity requirement?
No. So the simplest example that we have in mind is that of a static geometry where there's a time-like killing vector, and
that's fine. But as a spatial surface, is it convex?
As a spatial surface, is it convex?
Because if you imagine the contrary, you can have like two nested hemispheres which contain very little volume but have very large surface area. So other conjectures about generic entanglement, like in the bulk, like Takayanagi's surface state correspondence, they require convex surfaces only, otherwise it doesn't work.
Yeah, so let me try to understand the issue. Suppose that it's a star-like thing. Then you're saying that the area can be made. Yeah, what is the?
Yeah, I mean, I don't know a priori. I'm just asking whether you're assuming that. But what I was just thinking is that I can take like a football and I can push in one half of it deep inside, so it can have almost nothing inside it, but it still has a lot of area.
So the point is that for spherical spatial subregions, Bekenstein bound has been proved.
No, but spherical is convex, right? So I mean, that's exactly why I asked.
Right. And the thing to use which will probably somehow address your concern is to take the light sheet. So we are hoping to get some, instead of the area of the spatial subregion here, we are hoping to get the area of the light sheet, the entropy associated with the light sheet here in this equation 1, and which is something that Busso has also suggested to us. And perhaps, that might address the issue that you are asking, and also the issue that Subrat is asking. I'm not sure. Okay, that's an issue which we should also think of. Yes, but yes. Hi.
Yeah, sorry, Gautam, I have just going on this. There's also no minimization prescription here, right? So here is another example. Let's say we take a region on the boundary and take the Ryutakenagi surface that's bounded by that region on the boundary. But now I'll take my bulk region to coincide with the Ryutakenagi surface near the boundary. But as we go deep in the bulk, it does something arbitrary.
Okay.
So it's completely contained inside the Ryutakenagi surface, but as we go into the bulk, it kind of does something arbitrary. But right near the boundary, these two surfaces completely coincide. Now, your prescription would suggest that the entanglement of this would be different from the Ryutakenagi surface entanglement.
You would like to say that it is something which is our thing should be like a bound. Yeah, is that?
Yeah, okay. If it was a bound, then that might be, yeah. So if there was some, yeah, okay. If it was smaller than equal to, then that, maybe that was all. Yeah, I'm not even.
Yeah. So the way it appears in the in our argument kind of thing, the way it appears is that it is like a bound. So what we further want to say, whether the equality itself is true or not, by from the boundary prescription that we give.
So this is smaller. So the entanglement entropy is always smaller than equal to this. Is that the claim?
That is what I think we would be more comfortable with anyway, because that goes more along the lines of the Busso bound.
Okay, so that then it would be consistent with both the examples I gave, but in both cases, I think okay, true entanglement would be smaller, but this would still, be a valid bound.
Right. And I would also think about the convexity question. Thanks, Sunil. So, right. So now, so let's come to now a holographic quantity, which we'll discuss in some detail, and the boundary theory, which provides an exact non-perturbative definition of this entanglement entropy that we take as the definition of this entanglement entropy. And our conjecture is that when applied to weakly coupled gravity, reading large n, this holographic quantity should agree with this equation 1, and with perhaps all the other riders that have been pointed out in various remarks. Now, as remarked before, in a holographic theory, finiteness of the entanglement entropy is ensured by the finiteness of n, the finiteness of g appearing as the cutoff. We will find that this equation is qualitatively consistent with what one expects from the boundary theory. And I will explain what qualitatively consistent means. Now, the kind of quantity that we will propose for the holographic quantity, quantities of that kind have been, computed in some very extensive numerical calculations by Hanada et al. Sorry, I didn't put in everybody's name here, but later on I'll put in the more correct reference. So that kind of calculation will serve to provide a non-trivial test of a conjecture. Now let's go to the holographic definition of the bulk entanglement entropy. So we'll find below that the entanglement entropy of bulk subregion has a natural interpretation in terms of a certain subalgebra of operators in the boundary theory. Okay, and the choice of the subalgebra actually corresponds to partitioning of the target space of the boundary theory. So this is something that has also appeared in work by Mazink, along with some unpublished work by Shumit, me, and Sandeep. So here's the kind of picture that a boundary theory can be understood as a path integral of fields valued, so fields whose arguments are coordinates of this base space. Okay, so when one talks about entanglement entropy of a subregion of the base space, okay, then one has a partitioning of this kind. Excuse me. Partitioning of this kind, and so one does a partial trace over the degrees of freedom that are left over, and so that's what the usual entanglement entropy of a spatial subregion of the boundary theory is. Now, if it so happens that the range of values of this phi of x, so phi takes values, that is to say in a path integral, the range of phi, okay, corresponds to, so that's of course what is called a target space. Now let us say that corresponds to regions in the bulk. So if so this we'll see explicitly in the D0 brane example, that the range of these fields phi of x, okay, they will correspond to the base space of the bulk. Okay, so the so the base space of the gravity theory or whatever the bulk theory is, that will correspond to the target space here, and therefore a partitioning of the base space of the bulk theory would correspond to a partitioning of this kind of the target space of this theory. Okay, and we will explain how to exactly consider questions like reduced density matrices and so on in this context. Okay, so let's go. So before taking the most general question, let us get some guidance from one of the simplest models of holography, which is two-dimensional string theory, which is dual to a matrix quantum mechanics, which we have assumed here as gauged, so that we keep only the singlets sector of this quantum mechanics. So there's a gauged version of the C equal to 1 matrix model, and the matrix model is described by an action which is given in terms of an n by n matrix and an n by n gauge field AT, whose only job is to basically get rid of non-singlets. Okay, so you take this action, is written in terms of the trace here. So beta is some coupling, and n, a factor of n we have put in explicitly here. So basically, because of the trace, effectively there's an n here, and there's n. So the action is of order n squared. So the free energy, everything will be of order n squared. Leading contribution would be that. And in the AT equal to 0 gauge, there is still a residual symmetry of time independent UN rotations. So this will have basically M going to U dagger, and we can further fix it by going to a diagonal basis for M, which is this, in which case this out of the the global UN rotations, only the wild symmetry will be left over, will be left as the residual symmetry that permutes the eigenvalues, and the resulting theory has decoupled eigenvalues which behave like fermions under permutation. The action becomes that of n decoupled fermions in this way, and so the potential doesn't have to be something definitely given, but it has a local maximum and local quadratic maximum. Okay, That is what the main feature of this potential will be.
So
Okay.
excuse me, Takihiro, as my as for last line of the action, so may I understand that gauge fixed term is included in the potential V lambda, right? So I think there should be a gauge fixed term.
I'm sorry, you're talking about.
So may I understand that the gauge fixed term log sign is included in this potential, right? Potential V lambda I.
Are you talking about the Jacobian?
Yes.
Yeah, yeah.
Yes.
No, that is true. That is true. There is a Jacobian term, but if you do the time splitting correctly, what you will find is that the Jacobians in the intermediate time slices, they all cancel against each other, and then there is the Jacobian, which is the van der Monde determinant that is
Yes.
at the time initial time and left at the final time, and that multiplies the wave function of the symmetric wave function of the eigenvalues to make it completely antisymmetric. And that is how the harmonic nature comes. Yes, that is correct. So I have not detailed all that. So that's sort of.
So, but it in fact is included in the last line, right? It's
in this action, what you can do is to there are many ways of thinking about it. If you write the Hamiltonian to begin with in terms of this eigenvalues, then you will find that the eigenvalues are actually coupled with each other because the Hamiltonian is not a free Hamiltonian. But then you can make a change of variables by going to wave functions which get multiplied by van der Monde. Then the corresponding similarity transformation that you do on the Hamiltonian becomes that of a free Hamiltonian. We can discuss this.
Yes.
Yeah. Right. Okay. So so then so this was like in particles in fermionic particles in that potential V of lambda. And it can, of course, be written in terms of a second quantized fermionic theory. And this is how it looks like. And basically, there is the continuum theory of this model, which corresponds to string theory, is given by the following.
Sorry, Gautam, just one.
Yeah.
In this previous slide,
yeah.
So the last line should be something like, so these lambdas are complex formula. Isn't like del T lambda dagger, del T lambda? Is that what you mean here?
Del T lambda I, del T lambda I. Yes, that is correct.
I'm just trying to understand. So the lambda is a Grassmann odd. Or how are you thinking about this?
No. These are just to be thought of as this is the first quantized formulation, in which you just have, it's like xi dot square is all you have to make sure is that your think of this as just n particles, and then demand that your wave functions like psi of lambda 1 comma lambda 2 is equal to minus of psi of lambda 2 comma lambda 1. It's like, you can have a many-body description of fermionic theory or bosonic theory in terms of some first quantized Hamiltonian, which doesn't know about statistics.
Right. But I would think that, like the world line of a fermion would also have some Grassmann odd degrees of freedom. But okay, I think it's probably just a way of writing, maybe.
If I write this as a Hamiltonian, then you would be okay with that. So if I just have del lambda I whole square minus V of lambda I, that certainly would be a true statement. Then
I think it's probably fine. I think maybe, yeah, it's just.
Yeah, so I believe that I can write this also as this one. This is just a many-body representation of fermions, in which at the end of the day, you have to ensure that your Yeah, I think this is, certainly the Hamiltonian is correct. And I think the action is also correct in terms of the decoupled fermions. Yeah, so yeah, I'm not sure exactly what subtlety you are worried about. Yeah, we can talk about this. In my mind, it's all there in the wave function. Okay, all right. So in other words, I take eigenvalues. So in other words, I take the single particle action of the single particle Hamiltonian. I construct the wave functions, and I single particle wave functions, and I construct Slater determinant of these wave functions. That's my game. Okay. So now, so this is the second quantized formulation for that. And as I was saying, that depending on what this V of lambda is, so tuning beta does the following, that it changes the Fermi level. So for a given fixed number of n, where the Fermi level reaches depends on what beta is. So let me go to this thing, depends on what beta is. And there is a critical coupling beta C at which the Fermi level just reaches the hilltop, okay, reaches the local maximum. And you can take this double scaling limit in which, so n goes to infinity. And so near the top of the hill, the level density of states becomes infinity. So you have to take n going to infinity, and then beta going to beta C, or alternatively, the Fermi level goes to the top of the hill. So top of the hill here is being called epsilon C. And basically you take the following double scaled quantity that n goes to infinity, and epsilon C minus epsilon F times n remains some fixed quantity that's called mu. So the double scaled, so this is the double scaled Hamiltonian in which we have put in a chemical potential term which ensures that there are n number of fermions. In the double scale thing, that so this is the grand canonical description of that, which gives rise to a double scaled chemical potential mu here. And so now, so oscillations near the Fermi surface, okay, they behave, approximately like relativistic. So these are like density waves. They behave like approximately relativistic bosons when you express them in terms of the time of flight variable. So this is some, this is some sort of technicality which I don't want to spend too much time on. And those relativistic bosons approximately corresponds to the two-dimensional string theory scalar field, which was called tachyon those days. And roughly speaking, this is the correspondence. When the tachyon is expressed in terms of this x variable here, this is the time of flight variable, that corresponds to rho of lambda, or rather the fluctuation of the rho of lambda around its classical value. So so that's an entire history of this. But let's just take the following fact, okay, that the matrix model, which gives rise to the fermions, and the oscillations near the Fermi surface, small fluctuations near the Fermi surface, they behave like a relativistic boson. So if this statement is true, relativistic bosons moving in this X space, which is built out of this lambda space in this way, which is eventually it is related to the fact that the energy scale and the momentum scale, they are related by rescaling of this Fermi velocity. And the Fermi velocity here is something which is a local quantity, and that requires such integral that requires such rescaling between lambda and the original variable and the time of flight variable. So in terms of X, it's a relativistic boson, And therefore, if you ask now the following question, suppose I have an interval x1 to x2 in this X space, okay, which is originally the space of eigenvalues, okay. Now that has become, in the second quantized formulation, that has become one of the space-time coordinates. And if we have a relativistic boson of that kind, then it's given by the Calabrese-Ricciardi formula, which is just 1/3 log of x1 minus x2 divided by epsilon, where epsilon is some UV cutoff of the relativistic field theory. Now, it is easy to show that it is actually an artifact of the relativistic approximation, as we will very briefly explain now. So instead of using the relativistic boson approximation, if you go back to the original second quantized theory of non-relativistic fermions, what you get is the entanglement entropy is actually finite, and the role of epsilon is played by this G effective of X. So that's an X dependent quantity at the two endpoints of this interval, x1 and x2. And so G effective of X is given by 1/2 mu sin square X. So for lack of time, I'm not able to show you this, but this G effective of X actually corresponds to space-dependent coupling constant of the two-dimensional string theory. And so this is related to the appearance of G in our conjectured expression for the bulk entanglement entropy. The point that I want to make is that the this equation. Okay, so one thing to note that this equation is non-perturbative in string coupling, and the reason why you get this non-perturbative physics is the following in terms of the physics of the fermions, is that the.
So Gautam, just one point. This equation 2 you can never get from collective field theory, which is a hydrodynamic approximation to the original microscopic fermions. This is a very important point. Yeah.
Indeed, that's right. So this is a thing from which is non-perturbative from that from the point of view of the small fluctuations around the Fermi surface. And if you this calculation, excuse me. So this calculation, equation 2, had of the entanglement entropy in the non-relativistic fermion theory using the fermion second quantized fermion formulation was done by Schmidt in 1995, and more recently in this paper by Hartnell and Mazenk around 2015. So here so the one of the ways you can see that instead of, so where does this where does this finite coupling come from? It actually comes from the following, that if you just take the WKB wave functions which describe the relativistic bosons near the Fermi surface, then you would always get infinity here. But the point is that the WKB approximation breaks down if you take these points x1 and x2, the x1 equal to constant line and x2 equal to constant line way down here, then you will see that the oscillations will clearly reach or cross the turning point. And in that you have to really go back to the original fermionic theory, which knows about the finite depth of the Fermi surface. And it is these contributions which actually cancel the infinity that comes from this way, as has been shown in this paper by Hartnell and Mazenk in 2015, this cancellation. And
so Gautam, what happens to the double scaling limit actually, where the potential again becomes quite bottomless? And
yeah, so that's surprising. Yes, that's a very valid question. Surprising thing is that even in the double scaling limit, okay, there are contributions of this non-oscillatory parts or non-oscillatory corrections to the WKB wave function which manage to cancel the divergence. It's
the exact eigenfunctions.
Yes, that's a bit of a surprise. It's it's a bit like the thing that you and Anirban found, and also in our paper, that even in the double scaling limit, the fact that the left going and the right going wave functions so sort of talk to each other through the depth of the Fermi sea, somehow it comes. Okay, so anyway, so there's a lot of detail. So another way so this is one way in which has appeared in this paper of Hartnell of cancellation of the divergences. The other one is to realize that there is an exact bosonization of 1 + 1 dimensional logistic fermions, in which finite fermion number n translates to a finite UV energy cutoff. Okay, so it's a sort of non-local boson system, but you can show that finite number of fermions actually relates to finite UV energy cutoff. So that's another way of seeing that there would be an inbuilt energy cutoff in terms of in the theory coming from the finiteness of the fermion number. Okay, so that's this is what basically this demonstrates, that the finiteness of the rank of the matrix, which relates to the finiteness of the fermion number, and that eventually helps to sort of make finite this formula, which would have appeared in the naive approximation. And so now the point is that this was a rather
Gautam, can I ask?
Gautam, sorry.
Yes.
I'm again getting confused about this large n limit. So are you saying that in the infinite n limit it's actually divergent? Because you are emphasizing finite cutoff as arising out of finite n, right?
Yeah, actually finite n is not the finite n is not the right thing to say. I am actually taking a double scale limit here.
Yeah, so n is going to infinity, right?
N is going to infinity, but together with that, this Fermi surface, this actually also is reaching the top of the hill.
Yeah, okay.
Yeah. So
okay, so n is not finite really.
No. So the n, yeah. So I should say that it is the finiteness of So I should. So
double scaling.
Yeah, it's a double finite mu. It's a finite mu thing.
Okay.
Yes, thanks for the correction.
Okay, thank
you. Value of mu. So that's really the finite value of the string coupling. That is what I'm talking about. Yeah.
Okay.
Thank you. Right. Now, I just wanted to, close this equal to 1 part. Well, not close this aspect of this equal to 1 to say that this was rather fortunate here that, we addressed bulk entanglement entropy in a formulation of the matrix model in which we were still talking about a spatial subregion, because it so happened that the bulk, because there was an emergent direction coming from the sort of space of eigenvalues, which was automatically incorporated in this second quantized formulation. So there was an emergent space direction. So there was a formulation of the C equal to 1 matrix model, the second quantized one, in which the bulk space direction X appeared as the emergent space direction of the eigenvalues, so therefore one didn't have to do anything more. So space remains space. But this facility will not be generally available in more complicated example. For example, in the case of D0 deep plane models that we'll discuss later. And how would one compute? So the question would be that in the C equal to 1 matrix model itself, suppose I didn't use the second quantized formulation in which I was dealing with a field as a function of x and t. But suppose I dealt with the matrix model itself, okay, remaining in the first quantized formulation, and then how would one sort of define the target space, how to define the entanglement entropy of this bulk spatial subregion A. Okay, so here we will see now that it is possible, and the correct notion, as I have indicated before, is that of a target space entanglement entropy. And so we will do that, and then we will also show its equivalence to the second quantized computation of the entanglement entropy. Okay, so let me see how that goes. Now I would like to
ask just yeah. One question. So I was wondering, like what happens if I take, like this region to be big, like let's say 1/2 or something, like to this formula, this entanglement entropy formula, something funny happens, or
sorry, in this formula?
Yes, in the equation 2.
Yes.
So if I take, like your violet lines, I suppose, like to cover like half the. Yeah.
So what must be ensured is that x1 and x2, the entire interval, is far away from the turning point. Okay. So okay. That is when so in fact in this formula actually, x1 and x2 can be anything that you like, but here in this formula, okay, x1 and x2, because we wanted to apply WKB, they had to be the x2, like the rightmost line, okay, had to be far away from this from the turning point here. Okay. But in this one, x1 and x2 can be any negative number. Yeah, it can be any negative number.
So just to get an idea, this extreme is x1 equal to x equal to minus infinity. It goes from minus infinity to 0 and 0 to infinity. Is that how does x vary? Like in this diagram.
As a log lambda. Yeah. Sorry, I should take. I just let me just correct that. So x1 and x2 should be far away from where the Fermi surface. I still need that actually, excuse me, because I have used approximations of that sort in this formula, that on the Fermi surface, okay, x1 and x2, in particular x2, which is the rightmost, x2 should be far away from the turning point. Yeah, so you want to know how x1 and x2 look like in terms of the original eigenvalues directions. So this is actually the formula. It turns to be something like lambda is equal to something like cos x, okay, cos hyperbolic x, and roughly speaking, that means that x is like log lambda.
Okay, so so x goes from some log lambda. Okay.
Yeah, x goes basically from it actually goes from all over the real line. Okay. X does not have a cutoff. X does not have a cutoff. No.
So some like if you don't do this approximation, I think so. You're saying that in presenting this formula, you made an approximation that the interval is far away from the boundaries. Is that did I get that right?
That is right. But I should insist that there is an exact accurate formula for this one also, which can be written down by the method of this so-called cumulants, and for which it does not look as simple as this. But even that is finite, and it has other subdominant terms. Yeah, in this 1 over mu, in this 1 over mu expansion.
Okay.
Mu expansion.
So I mean, just to address like some of these discussions that we had, like a few minutes ago, like has anybody studied what happens if one of them reaches the boundary or something like that? Like
one of them reaches this point here, the turning point.
No, the other end.
Oh, this end.
Yeah.
This end is actually at infinity. Okay, so this is only a cartoon. So what happens is that in the double scale limit, okay, this cutoff, okay, it can be let go to infinity. Yeah. So, oh, you were worried about the cramping from the other side. No, there is no cramping from the other side. This cutoff just goes to infinity.
So should I think of the C equal to 1 matrix model as living there or something?
C equal to 1 matrix model as basically the variables of the C equal to 1 matrix model can be thought of as living here as well as here on the two, in the two Fermices or around, even all the way up to here. Or some people put an arbitrary cutoff at x equal to 0 and make it a one-sided model.
I was thinking of some holography kind of things where we think of CFT as living in the boundary. Of course, in some sense, CFT is living everywhere in ADS.
Yeah, the boundary aspect, the holography aspect of C equal to 1 matrix model is, yeah, so I should say that there is an understanding of the C equal to 1 matrix model, the gauged version of the C equal to 1 matrix model in terms of the unstable D0 branes in type 2, the two-dimensional type 2 super string theories. And it is in that context that it's sort of similar to the thing that I'm going to discuss, D0 branes in 10-dimensional space-time. So this is the two-dimensional version of that. So you can, yeah, so it's a little more contrived to go from this direction to say that whether the eigenvalue direction itself is a holographic direction. That's what you have in mind, right?
Yeah, sometimes the matrix model, you can kind of, mimic it like ADS CFT, right? Like you can think of the model as itself as living at infinity.
Indeed, that is right. But there are issues with thinking of the eigenvalue direction as a holographic direction, which I don't have the time to go into these details.
I'm sorry, but Gautam, I mean, as you know very well, that there is an exact formulation in terms of phase space variables in which you can really cast the C equal to 1 matrix model in a way in which holography to the tachyon equation of two-dimensional string theory is manifest.
That is right. That is right, Spencer. The thing is that
the only thing sorry. Please continue. I think we don't want to get caught on C equal to 1 now.
Yeah. No, that's right. That's right. I mean, that's a constraint variable. So what Spencer is saying is that there is a 2 plus 1 dimensional bosonization available in terms of the Wigner phase space distribution of these fermions, and that actually remains an exact bosonization, and in terms of which it's an exact formulation, but of course you have to put in those the Lake-Pole factors and some other things in that formulation. It can be made more natural. Yeah, this is a long story. I mean, I just wanted to be, I just wanted to some,
Yeah, Gautam, I guess what I wanted to know without dragging everybody into the technicalities of the C equal to 1 matrix model is that, is there a way to address in this setup kind of question that were being raised, like in the beginning of the talk? About having intervals which include the boundary and so on. So
yes.
That's all I wanted to know.
Yeah. That's a very important question. So where maybe it's a kind of, so you might ask, is this like the bulk entanglement entropy term, for some scalar fields in the bulk only, or is there some area over 4G Newton also like happens in JT gravity and so on? So those questions we are not addressing here. I mean, nor do we know whether this is the correct setup to do this, and whether this eigenvalue direction in all senses is a holographic direction. Yeah.
Gautam, the C equal to 1 matrix model, as you have described it, there is no real dynamical gravity. I mean, there's just a flat space-time with a linear dilaton.
Yeah, you might ask the following questions, Venta. That just like in JT gravity, one has an expression for Ryu-Tak energy. Okay, that the area over 4 G Newton, that's given by the dilaton, the value of the dilaton, and then there is there is some sort of thing that you can mimic, which is like holography. Let me go to this D0 brane.
Yeah. Sorry to interrupt.
This is like D0 brane. This is like D0 branes in 2D supergravity, really, and
yeah.
I mean, yeah, okay. In spirit, what you were saying, Loga, is true. That I should be able to think of this this emergent direction as the holographic direction.
Yeah. So,
and I'm only sort of I only have some technical problem in pushing that through.
Yeah, just to I'll just write up, but I think what I was asking was something like at some point I think Rajesh had a paper describing, at least for the Gaussian matrix model, how you might want to think about it in the ADS-CFT way, and how do you but something like that, whether C equal to 1 can be extended to C equal to 1 matrix model. That's a kind of question I was asking.
No, that's a very, very, very good question. And there should be an understanding of that kind of the C equal to 1 matrix model. For example, this question itself that we're asking, whether we can really clinch it, that there is this conjectured bulk entanglement entropy of the form that we have said in the beginning of the talk, whether that can be matched with what we are getting here, and whether we have a sort of boundary derivation of that formula. What we have a boundary derivation of is of equation 2. Okay, but how to compare that with our equation 1, which was given by this area divided by 4 G Newton, that's not clear. Okay, so all very good questions. Okay, now, so as I said that I have to go to this, and unfortunately I have to change my mode a little bit now. So what I have to do is to, okay, just give me 1 second. Yeah, can everybody see it now? Hello?
Yes, we can see it.
Yes.
Okay, so unfortunately the the equations here were a little complicated, so I just wrote it by hand. Excuse my handwriting. So by the way, I have already crossed 1 hour. How much time do I have?
Maybe 10 minutes more.
Okay, all right. So this is actually one of, like the heart of the matter. So let me just spend maybe a few minutes on this. So target space entanglement entropy, we will ask how to define this. For the quantum mechanics of n particles, to begin with, we will consider distinguishable particles, distinguishable particles. And so a general one particle wave function is given basically by, in terms of the x basis, in terms of the amplitude psi of x. And this integral can be split into 2 regions, A and A bar. Okay, which, so A is a subset of R. And clearly this kind of a split says that the one particle Hilbert space is a direct sum of HA and HA bar, where HA is given by the span of the X ket with X in A, and H A bar is the span of the X ket with X belonging to okay. So this is what it is. And so note that this equation 4 is a direct sum and not a tensor product, so that the usual operation like, that you do for partial tracing, trace over H of A bar, does not seem to appear to be available. But the appropriate notion turns out to be here to define an operator algebra, okay, which I call script A, labeled by A, which consists of operators that acts non-trivially in the region A, that is to say on the kets X. Oh, thank you. All right. So somebody has put a thing here. Okay, all right. So which acts non-trivially on the kets X, where X belongs to A, and operators which act trivially on the kets X, where X belongs to A bar. Okay, can somebody get rid of the doodle here? Joel, are you the host? You can probably get rid of the doodle. I'm not able to, sorry, I'm not able to get rid of this.
I think one should be able to just, Joel, you should be able to just clean the code or something, clear it.
Okay, anyway, let me carry on. So the operator algebra consists of operators like this, okay, whose matrix elements are of a block diagonal form. So when X and X bar are both in A, then it's a non-trivial operator, and the off block diagonals are 0. And when the matrix elements are X and X bar are both in A bar, then it's just a delta function. So acting on the state X, it retains the state X, perhaps multiplied by a number O0, which is just a constant throughout this block. So this clearly would correspond to a partitioning of the target space, which is reflected in this operator algebra. And the reduced density matrix with respect to this operator algebra is defined by the unique operator rho tilde belonging to this algebra, which satisfies the trace of rho tilde O is given by trace of rho O, where rho is the original state of the system, such as pure state, psi like this, or some mixed state, etc. And we ask the question that on this operator algebra, when O belongs to this operator algebra, is there some rho tilde which satisfies this equality? And once I'm done with finding that rho tilde, I'll just take the reduced density matrix. I mean, I'll take the Formulation entropy of that, and that will give me the thing. And indeed, the answer to this is simply this. For the one particle Hilbert space, it's just given by the original rho XX prime in the AA part of the block, and it just some identity operator in the A bar part of the block, given by some rho naught, which is just an integral of rho XX in the A bar region. Okay, this is really easy to do. If I was doing it on a blackboard, I would have derived this. It follows from the simple identity that the original rho XX prime with the delta function and O naught, okay, on the A bar is just given by this thing. So this is really easy. I mean, you should be able to check this. Okay, now we do this exercise here for two particles, and for two particles. Okay, I don't have time for this. Let me just tell you the formula for the two fermions. Okay, for the two fermion Hilbert space, there are sectors like H20 where both fermions are in region A, 1, 1, in which one is in region A, the other one is region A bar, and 0, 2 is in which both fermions are in region 2. The operator algebra has a block diagonal form, the obvious kind of block diagonal form, again like that, and the row here, the reduced density matrix, has also a block diagonal form, and so it's explicitly writable. So this I have written this in terms of a row which is given by a pure state density matrix where the pure state is a Slater determinant, and so in which case you can write down in each block the density matrix and so on, and you can write down a formula for this density matrix. Okay, and we have, in specific cases, we have in fact done the we have done this thing that, and for the n fermions also I have just written down here explicitly this reduced density matrix in terms of some determinantal structure, and the final target space entanglement entropy is given by this stuff. Okay, so the this can be seen to be this calculation can be identified with a second quantization when the second quantization is of this thing is available, and you can, so the various sectors of the Fock space. So the original tensor product decomposition of the Fock space means that there is a sector-wise tensor product decomposition of this first quantized theory, and using that you can show that this actually is this is independent of, I mean, the first quantized answer and the second quantized answer are the same. Okay, so let me go back to this this thing again, to the full screen mode, and the okay, so we do this for the yeah, so for the D0 brains, what we do is to, okay, so there's a, because of the lack of time, let me just do this, that there is a geometry of the ADS CFT of D0 brains was calculated, was laid out by the paper of Itzhaki, Maldacena, Sonnenschein, and Yankelowicz of 1998. And so this is the geometry, and the supergravity description was actually valid between a certain minimum and maximum radius of R, beyond which either the dilaton or the string scale curvature became large. And so what we do is to take this geometry and compute our area divided by 4 Newton in a for a planar partition of this kind, x1 equal to d. So what we find is that the
Gautam, perhaps we can make it full screen completely. I think I'm not able to see the full slide.
Oh, sorry.
Yeah, this is fine.
Okay. Thank you. Yeah, because I never know who is being able to see what. Okay, so this is the my region A is the bulk region A is x1 greater than d. So there are these besides time t, there are these 9 coordinates x1 to x9, and I take a planar partition given by x1 equal to d. So x1 greater than d is my region A. That's the region of interest, and if you just take the area of this surface, then the area of the surface is actually infrared divergent. So it has some, which you can regard as being cut off by the R max. And although this gives us a finite answer, it's not precise. So what you can do, on the other hand, is to take a small, black hole in this background corresponding to a certain temperature. So that's a thermal D0 background. And if you take the entropy at finite temperature minus the entropy at T equal to 0, then you get some exact result here. Okay. So the here comes the important thing that it's given by the following parameters. One is the radius of the horizon, which is given in terms of the temperature, and then there is the there's R, which is the ADS radius, and Newton constant, and then D. What we will do is the following. We will write all of these quantities in terms of appropriate dimensionless quantity. Okay, so in this, taking Q from the D0 brane matrix model, which is what we are going to compare this with, we will find that the correct length scale is something that is given by the kind of lambda QCD for the D0 brane matrix model, which is given by this quantity, GSN to the power 1/3 divided by LS. And that's the only length scale that is there in that D0 brane quantum mechanics. And if we and we also take this thing that transverse distances to the brane, okay, are also related to the energy scale and not some corresponding to it. So the transverse distances to the length thing are given by the energy scale itself according to radius CFT, and parallel length dimensions along the brane are given by inverse of lambda. Okay. Using that, what happens, very surprisingly, is that all factors of G string cancel in this quantity, and you are left with something which are given by just dimensionless temperature and dimensionless distance, and times n square, and some number here which can be explicitly computed. Okay, this is the kind of expression that you would expect to get from the D0 brane matrix quantum mechanics if there were lingering factors of GS. Okay, then it would not have any interpretation here, because basically dimensional transmutation says that if you express all dimensionful quantities in terms of ratios with respect to the lambda QCD, then there should not be any coupling constant left over. And that's precisely what happens in this quantity. And if you apply it, if you use the string length as the cutoff, then actually this does not happen. And there are some factors of G string that hang around. Okay, so you can do a similar analysis with DP branes. The same thing happens, that if you use the G Newton as a cutoff, then only dimensionless quantities survive, and all factors of G string, they cancel out. Okay. And so let me just say very quickly that in D0 brane quantum mechanics, we have been able to identify the target space entanglement entropy by considering an operator algebra, which let me just say in very quick detail. Once again, we diagonalize the matrix, but only one matrix we are able to diagonalize, of course, which is X1. And so here various sectors are given by, so let's say if X1 greater than D is the bulk region that we are interested in, then we look for how many eigenvalues are greater than D and how many eigenvalues are less than D. Those are the various sectors that define for us the sectors of the Hilbert space, which have these reduced density matrices. And we need a prescription of what to do with the off-diagonal variables. So we have two alternative prescriptions. One in which the off-diagonal elements which are straddling between the region of interest A and that of its complement, okay, in one prescription, we don't keep them. They are part of my unobservables on operators, so they are not part of my operator algebra. And we have some explicit explicit expression for the reduced density matrix using that. And the other prescription is in which we do include them. Okay, so so both are explicitly calculable numerically, which we have not done. And however, you can show that the form of the entanglement entropy that you get is indeed of the form that I had said before in the context of the geometry, that it is n squared times a function of T naught and D naught. So that's what it is. So let me say that one can set up this calculation pretty much in the same way as the calculation by Hanada et al. Hanada, Yutake, Ishiki, and Shimura, and these people in 2016. And we are also sort of setting up for the particle problem, not for the matrix problem, a replica trick calculation in the target space. Okay, and so I will skip these things. So it's the concluding remarks. I propose that entanglement entropy of bulk regions map to target space entanglement, and this quantity should be calculable numerically. We are setting up a replicative method to make this possible in simpler cases. And we conjecture that the leading answer saturates the area law. This means that in a UV complete theory of gravity, the cutoff in the entanglement entropy is provided by Newton constant, and the target space entanglement entropy is defined for all values of the parameters T naught, D naught, N. It may be possible to see how this quantity changes beyond the regime. So as I said, this target space quantity is defined non-perturbatively and beyond the regime of weakly coupled gravitons. In particular, for finite n and higher T naught, bulk locality fails, and string and loop corrections become important. These are related to some of the questions that people have asked, in particular Surat has asked. But the target space entanglement entropy does continue to make sense. Thank you very much. Sorry for being over time.
All right. So thank you very much for the nice talk. If you have any question, please go ahead.
Gautam, in your D0 brain metric
Yes.
ansatz, you actually were talking about finite temperature geometry, right?
Yes, right.
So, okay, a little bit confused because, if I were to discuss entanglement entropy,
yes,
I would in general be talking about a density matrix at 0 temperature. So
no. I could start with the density matrix to begin with. The total system could also be discussed with the density matrix, and then I can have a bipartition of that. And yeah, it's not necessary to start with the pure state density matrix of the total system. I could have a I mean, that would correspond to the notion of thermal entanglement, in which
that's what's worrying.
No, so that can be calculated. So in the D0 brain quantum mechanics also we have to do that calculation. That is how we have set it up. That we should take the original density matrix of the system itself to be a thermal density matrix, and do a bipartitioning of that, and so on. So there'll be in such cases they call what they call is the quantum entanglement and classical or thermal entanglement. So, yeah, that can be done.
Okay, thank you.
Any more questions?
Sorry, Gautam, in this D0 brain calculation, maybe I'm kind of not very clear about it. So is there a place where you get area by 4G Newton?
Yeah. So in the D0 bulk calculation, that's what we compute. Okay. Now, and that gives you, so basically, okay, that I went on to that a bit too fast. So what happens is that the area term is the area of this surface, okay? And the area of the surface, of course, is infinity. Excuse me. In the original D0 brane geometry, which is this one, because it's just that the measure is infinity here. But the point, so there is one way of thinking of that infinity is that the supergravity description itself breaks down when it is too far away from this r equal to 0. And so if there is a natural cutoff given for this area integral to be done, given by this R max, which was given by GSN to the power 1/3 times LS, that was in this thing that there is an R max. And however, you might say that, well, I'm putting this cutoff, and is it equal to the cutoff, or is it of the order of the cutoff, and so on. So it does give us a finite answer, but it's not precise. So there are two ways that we found that you can get a finite answer. One is to stagger, one is to have a distribution of these D0 branes. Okay, so there's a multi-centered D0 brane geometry, and to adjust them in such a way that the fall off is sufficiently fast, so that the metric here has sufficiently fast fall off, so that the area is. And the other one is this temperature. So you take a thermal D0 brane background, so that's a black hole, and so that the area is divergent, of course. And then the T equal to 0 contribution, which is also divergent, the same divergence that we talked about. And if you subtract that, what you will get is this thing. This is the Einstein metric area. It's not easy to see that this is the area, but if I have a blackboard, then I could do this. And there is the 4 G Newton sitting here. Okay. And all we say, yeah, sorry, go ahead.
So and the question and the statement is that this can be, if you could compute it within the D0 brane matrix model, you could get this answer. Is that the claim?
That is what the test is. Yes, that is what we would like to say, that if it could be done in just like Hanada et al. Had done their matching between supergravity, the D0 brane matrix black hole calculation, and this one, the free energy matching in the appropriate regime. That is to say, in the large N, sort of giving defining what approximations are going on, so that they could compare with supergravity. That is what is to be done in this case also. And once one does that, the quantity to be computed, of course, is quite clear. We have written this. Yeah, indeed, that's right. So the von Neumann entropy of the reduced density matrix should give you this. I mean, the subtracted quantity.
But there you should do some separation of algebras, like you had described in C equal to 1 matrix model.
Yeah, that's right. That's right. Indeed.
And is that clear? How do you do that separation in the?
Yeah. So so there are two possibilities. Yeah. That now so sorry, I went over this a bit too fast. So let us say I have only 2 matrices instead of 9 matrices, and these are 3 by 3 matrices.
But for Gautam, if I just wanted to compare with what you had calculated with this thermal guy, so then I would have like n number of matrices on one side.
Yeah, right.
Sorry, n D0 branes on one side, and then you would have no D0 brane on the other side. Is that correct? And
so there will be no, there will be configurations in which there will be n-1. I see. You're talking about the classical background. No. So good. sorry, I'm talking about not the class. In the classical background, I have a single centered thing and so on. But this wave function actually has a spread. Okay, it actually has a largish spread. So that those remarks all went in. Here it is. So there is a Coulomb branch where you know this let's say the first in fact all xi's are diagonal, which correspond to coordinates of n d0 planes, and so it is that thing that says that the base space of the gravitational theory becomes target space of this quantum mechanics, and the gravity solution. But the point is that, yeah, the gravity solution that we wrote is indeed at the origin of the Coulomb branch, everybody together, but the wave function has a spread, okay, of this much, which can be, sort of argued up to order 1, or it can be calculated as I had done in a paper with Mahato and Morita in the large D bosonic BFSS matrix model, where you can show this. The number also you can compute here, and
sorry, what is the calculation I should do? I should kind of find the wave function on the target space.
You should do the following calculation. Let us say in pure state. In the pure state, yeah. So what you should do is, so this is your wave function. Let's say, okay. In a pure state. And there'll be in the density matrix, it will be psi ket psi bra corresponding to this. And a general operator is given by this. Now you have to pick the algebra of operators that corresponds to the partitioning of the gravity, of the bulk space that I talked to. So that kind of operator would be like, so in case of the C equal to 1 matrix model, I already did that. Okay, there were only eigenvalues here. So the eigenvalues, the non-trivial matrix elements were only lambda I and lambda I prime, when both of lambda I prime were in the region A. Okay, and when lambda I and lambda I prime were region A bar, it was a delta function of lambda minus lambda. You have to do a similar analysis here. Here, one of the matrices you can diagonalize, and we have taken the partition also according to that specification. So we have said we want to say that x1 is greater than d. Okay, so let us therefore diagonalize the matrix capital X1 also, and then we ask ourselves that in various sectors, like let us say that there are two, this is a 2 by 2 matrix. Okay, so then if both, now there are, this are like, yeah. So I didn't really, yeah. So the point is that there is a way you can have this block diagonal structure of this operator algebra. Okay, depending on how many eigenvalues are less than d and how many eigenvalues are greater than d. Okay, but additionally, you have to say what you are going to do about this. So so here's the picture. Okay, so this is the situation. This is the 2,1. So this is a 2,1 sector. Excuse me. So in which the degrees of freedom are what is written here. Okay, and so it's so this is the one in which lambda 3 is in the A complement region, and lambda 1 and lambda 2 are in the region A. Okay, so this is how you define your operator algebra that you are interested in. You can measure states which have lambda 1, lambda 2 ket, where lambda 1, lambda 3, lambda 2, lambda 3 ket, and where you are interested in only in operators of this kind, okay, which involve lambda 1 and lambda 2 because they are in region A. But you also have to say what you are doing with the off diagonals here. Okay. So the off diagonals have this picture, okay, that, so you want to say that, I want to say that this operator in the operator algebra certainly should include the open string connecting, the second D brane, okay, and the first D brane, and the second D brane, and so on. And but the first to third and the second to third, okay, these, whether you want to keep it in your operator algebra or not, that's not immediately clear. Certainly this guy, okay, the one that that's a 3-3 open string, that you should discard, okay, because your detectors are here in the shaded region, okay. So we have one prescription in which we ignore the straddlers, and we keep them, we ignore this, and we have another prescription in which we keep this. Okay. And in both cases, finding out this reduced density matrices is quite easy in principle, and it's given in terms of some integrals, and then you have to do the Formulation entropy of them, perhaps through Arrhenius entropy.
But okay, one thing I was wondering about is that what happened to all the gauge invariants and so on and so forth? You've diagonalized one of the X matrices.
Yes.
Using the gauge transformations.
That is right. And then there are the only thing that is left over, still left, is the Weil transformations, and you have to take them into account. So in each of these, your wave functions are actually given by a certain number of or the density matrices are given by this set of eigenvalues. The set of eigenvalues and the off diagonals, plus to each of them you have to add their Weil images. Okay.
So by Weil transformations, you mean the Weil reflections? Is that? Yeah.
That's right.
Permutations, the permutations of the eigenvalues.
The permutations, on eigenvalues, they act as permutations. And on diagonals, they act a little more distinct. For example, in this one, it's lambda1 and lambda2 are interchanged, and x11 is interchanged with x12, and x12 is interchanged with x21. Okay, so this is how it.
So what happened to the Gauss constraint? Why is it Gauss constraint creating some issue that?
We are dealing with at the level of the wave function, and so the Gauss constraint is good. So the Gauss constraint actually is the same as the SUN invariance condition.
Yes.
So you know that x1, so x basically is x mu comma p mu acting on the wave function is 0. So what happens is that it's a commutator of x and x dot that becomes divergence of, that becomes the equivalent of divergence of E. And so commutator of x and x dot acting on the wave function equal to 0 is the same condition that is an SUN singlet.
Yes, yes.
So as long as you have,
So I'm just asking, where is the singlet projection condition? I think that's I agree that that's an equivalent statement. So where?
So if I have already diagonalized one of these x1 fellows, to the eigenvalues, and then of course you have taken one point of the orbit of SUN. Okay, so you can show that. So you might want to say that I should do a sum over all points of the orbit to get a wave function which satisfies Gauss law. Okay, in principle that's what you should do, but that integral actually comes out of the various formulas because of invariances. Yeah, the formulas that the quantities that we compute, they can be computed at just representative points of the SUN orbits.
Okay, maybe. Sorry to bug you, but I would have thought that like you would get into the same trouble that one has when we think about gauge theories, right? Where like when we think about, I mean, because of the Gauss constraint, there's no simple factorization. So I would think that the singlet condition, the SUN singlet condition, will be on the total space, and the kind of like the strings that you're drawing, like you have to kind of do them with some care, but you're saying that that's not necessary. I'm just trying to understand, like, why is there no center and so on and so forth, like in this in this interface. Why don't I have to worry about all that things that we worry about in the lattice gauge theory if you want to define a reduced density matrix or a entanglement entropy?
Yeah, well, this is actually yeah, this is actually target space, in so all the gauge theory complications, that kind of complications would have appeared in the in some field theory in the bulk itself. This guy, in the complications of gauge theory in the matrix model, are just rather too small, very small. There is a gauged quantum mechanics that is going on, of course, but that you can handle. So you are right that if there was a bulk gauge theory in which this was like a space subregion, and this was like a Wilson line and so on, but that's not really it. Or maybe it's this, the first quantized theory is just oblivious of that. But the kind of gauge theory complication that comes from Gauss law here can be handled, and we have handled them.
Okay. Thanks.
There is no complication.
Yeah. Yeah. Thanks.
Any more questions? All right, so it seems that there is no more questions. So thank you very much, Professor Mandal, and thanks everyone for attending this talk. So before we call it a day, I want to announce that on 22nd May, we have a seminar by Juan Maldacena. So those who have subscribed in our mailing list, so we will send email in due time. So I wish you a nice time and see you on 22nd May.